All right, let's look at the standing waves of a string. All right, let's say you have a string and say maybe fixed on one end, and you have some sort of oscillator or just spinning it around like a jumping ropes, so that it's going to create standing waves. Right, so this is going to be the rope and a standing wave, and we'd like to set up a differential equation for this standing wave. All right, so before we get into a standing wave equation, we're gonna review this centripetal force. All right, let's say you have a mass m going around in a circle counterclockwise with the radius r. All right, so we can express the position of this mass as r cosine of omega t comma r sine of omega t. Let's say that's the position function. All right, then we can take the first derivative, which gives you a negative omega r sine of omega t comma omega r cosine of omega t. So this is going to be the velocity function of this mass. All right, so you take another derivative, you end up getting a negative omega square r cosine of omega t comma negative omega square r sine of omega t. This is the acceleration vector. All right, so I'm going to go ahead and take the magnitude of the acceleration, and you end up getting omega square r. All right, and remember that centripetal force is toward the center of the circle, and a force is mass times acceleration. So simply, since the acceleration is omega square r, so we know that the m times omega square r gives you m omega square r. All right, so let's keep in mind that the centripetal force can be found by mass times omega squared times radius. All right, so let's go back to the standing wave of a string. All right, so this purple curve is a string, and we're going to assume that the tension on the spring is uniform throughout, so it's the same tension everywhere. All right, then what we're going to do is we're going to just focus on just a small piece, say of length delta x. So we're looking at just one piece right here. All right, just small piece. All right, and so we since it's the tension is uniform, so on this right end, it's pulling toward the tangent direction of this string this way, and on the other end, same tension is pulling in the tangent direction. And what we're going to do is we're going to look at only the vertical component of that force. All right, so the vertical component of, say, right end is going to be, I'm going to give an angle here. Angle here is going to be theta 2, and angle here is going to be theta 1. All right, so the vertical component at the right end point is going to be, you can simply multiply by sine of theta. So we have tension times sine of theta 2. So this is the vertical component upward, right? And if you look at the left end point, so it's pulling downward, so this is going to be tension times sine of theta 1, all right? So the difference between those two forces is going to be equal to the centripetal force. So we can set up an equation. So we have, so this is the upward force. So T sine of theta 2. And this is a downward force. So T sine of theta 1. All right. Since we're assuming that theta 1 and theta 2 are fairly small, so cosine of small angle is very close to 1. So we're going to do this following approximation. We're going to actually, instead of sine, we're going to use tangent. So here, first I'm going to pull out the t. so that actually maybe that I should write the equality there. So this is going to be equal to t is pulled out, and you have a sine of theta 2 minus sine of theta 1, right? Then since cosine of theta 1 and cosine of theta 2 are very close to 1, so I'm going to approximate sine by tangent. So you have a tangent of theta 2 minus tangent of theta 1. Right? So since the sine of theta and the tangent theta are very close to each other when angle is small. All right. The reason why I wanted to do that approximation is that we can view tangent. So tangent is opposite over adjacent, which is same thing as rise over run. So it actually is the same thing as slope at that point. So if you look at here, t, and tangent of theta 2, so that's going to be the slope of the tangent line at x plus delta x. So if you want, say, I'm going to call y. So y is the position of the string. So you have a y prime of x plus delta x will give you the slope of the tangent line, right? Because derivative always tells you about the slope of the tangent line. So we're going to have y prime of x plus delta x. And if you interpret tangent of theta 1, it's the same thing. It's going to be the slope of the tangent line at x. So it's going to be minus y prime of x. Right? So we get that. Then what we want to do is this is going to be equal to the centripetal force, right? So let's look at write the centripetal force. So it's going to be, right, centripetal force is toward the middle, right? Then in this case, let's say I didn't mention, but let's say the density of this rope. It's a linear density, let's say rho, right? Rho is the density of the rope. All right. Then if you want to find the centripetal force, we have to find a mass, right? So mass is going to be of this piece is going to be density is rho. The length is going to be delta x. So we're going to just use that as let's say this is going to be a negative direction, and the mass is rho times delta x, right? All right, and then omega squared, so that's the frequency squared, right? And r is just going to be the y value, so it's going to be simply y, right? So we can set up this type of equation. And what we're going to do is we're going to divide through by delta x, right? So we're going to have divide through by delta x. We get t times y prime x plus delta x minus y prime of x divided by delta x, and this is going to be equal to negative rho omega squared y, right? And as delta x, we're going to send delta x approach 0. Then you can see that this is just a difference quotient, so it's going to be the derivative. So it's a derivative of the first derivative, so this becomes just a t y double prime. And I'm going to move this term over to the other side. So it's going to be plus rho omega squared y, and is equal to 0. So I added rho omega squared y. All right, then I'm going to actually just divide through by t. All right, then you get y double prime plus rho omega squared over ty is equal to 0. All right, then we actually can add boundary condition. Right, so here in the beginning it's 0 and at the end it's also 0, so we can say y of 0 is going to be 0, right, and y of L is going to be equal to 0, right. Then you can see that this is actually a boundary value problem, and this is actually an eigen. So this is going to be a boundary problem. And if you think of this right here, this guy as lambda, and this is actually eigenvalue problem. So this is the eigenvalue problem. Right? So we could use a little bit of physics to cook up a differential equation, which happens to be an eigenvalue problem. All right, that's it. I hope that this was clear.